Welcome, grade 11s. Yes, you are here with me, Megs, and of course, my lovely lady, Tracy. But we haven't been together in so long. It's so sad.
I know.
So
It's
tragic.
crazy.
Please tell me what we're doing today.
Today, we are going to go through forces and Newton's laws. And as we were talking just before the break, it's really, really a critical section of work, and it's a section of work that students often struggle with. So today is
Like
a good one to tune in.
Like I told Tracy just before we started, Newton's laws were not my favorite, but they are really important. Definitions, most important, as well as arrows and this and vector and this and everything. So I suggest you grade 11s take note, because especially for matric, this is a section that hits you hard, I promise you. But anyway, I have to tell you about the Samsung Learning Hub app that has been sponsored by Samsung, obviously, powered and sponsored proudly with Learn Extra Mindset. So let me just show you how it works, what it's all about. It's the Learning Hub. You guys have heard about it. Free content as well as new content updated every single day. So here you can see it's physical sciences, and I'm sorry, but Tracy's just a little bit there. So here we have the notes on this side, obviously, and the video. So how amazing is that? You get content, you test yourself for revision, and the video you can watch on the lesson. That's really, really cool. Other than that, guys, it's only for premium smartphones and Samsung tablets. But stress, not mindset, is because you know about the Learn Extra Exam Revision Marathon Competition, right? Yes, you do, because all you have to do is download the notes. I'll post the link for you now, and you click on the race number, you look at it at the bottom of the notes, and then you enter it into the link. Okay, the link will be posted on Facebook as well as the revision notes where you have to find them. So it's basic, it's easy. You enter your name once and you get thrown into 9 draws. How amazing is that? So it's awesome, cool. You could stand a chance to win yourself a tablet. So then you can actually download the Learning Hub app. How cool is that? So without me just rambling on about this, Tracy's going to take it away with Newton.
Thanks so much, Megan. So we're going to be carrying on with forces and Newton's laws. Let's get straight into this. In this lesson, we're going to revise how to work with vectors. And vectors are something that students often say to me, I can't stand vectors. Vectors are so useful. But you've got to know how to interpret them and how to use them. And then we're going to be looking at applying Newton's laws to a whole bunch of different scenarios. Specifically, we're going to be tackling questions. So let's get straight into it, because I know grade 11 revision, this is very important for you. So we have been given 2 force vectors. This is question 1. There are force vectors. So immediately you're going to be thinking to yourself, whatever units I have here are going to be, the units will be in newtons, okay, N. The force vectors P and Q were drawn to scale on the Cartesian plane. The fact that they are drawn to scale is also something very important. It means I can take the measurements from them, which is very valuable. Use a calculation to determine each of the following: the magnitude of the vector P in force units. So, having a look at this diagram, I've got quite a bunch of information. Let's have a look at it. This first one, and I'm going to draw it in blue, draw over it, that is vector P. All right? And it says to me, use a calculation to work out the magnitude of vector P in force units. Well, what do I have? I basically have, and I'm going to sketch it for us here, I basically have, if that is P, I'm going to work out the bottom of this triangle is in 2 units, and the side of the triangle going up there is 4. I'm just reading off those values off the graph. So if I sketch that again, and I'm literally just sketching, this side was 2 and that side was 4, I can work out the magnitude of the vector P. The magnitude I'm going to work out through Pythag. Okay, Pythagoras, all right, you know it. R squared is equal to x squared. R squared is equal to x squared plus y squared. What do I have? I had x was 2 squared plus y was 4 squared let's work that out. Well, 2 squared is going to be 4, plus 4 squared is 16, is 20. Is that my final answer? No, it's not my final answer. I need to say, well, r, which in this case is actually p, is going to be the square root of 20, and I can't leave my answer like that. I have to square root it and show it in surd form. And so we go to our calculator and say square root 20 is equal to, and I don't leave my answer like that, I write it as a decimal, 4,47. So 4.47 in force units, newtons. The direction of vector q is the next thing I need to calculate. So I'm now going to be asked to calculate, that is theta, the direction q, measured clockwise from the positive axis. So once again, I'm going to sketch this, and q went off somewhere this way. And if I have my axes labels, this side was going to be theta, and we've got some values. I know this one down there is how much? That is going down to 1, so it's minus 1, and across minus 3, and going across by minus 3. So let's just put arrows on those. So notice I've split that into its components, all right? Taken the whole vector that's going at an angle and I've divided it into its components. The direction of the vector. Well, now that I've drawn a simple triangle, I can work with each of those values quite easily, because what I can do is I can say, all right, opposite over hypotenuse, or adjacent over hypotenuse, or the values that I have here are opposite over adjacent. What trig ratio is that? You should be thinking that trig ratio is going to be tan of theta is equal to opposite over adjacent. So from where where theta is, it's going to be opposite over adjacent. So it's going to be minus 3 over minus 1. And we have therefore theta is equal to. So I go to my calculator. Let's clear all of this. I'm going to say second function. So shift sine. So sine, there it is sine. Oh, sorry, not sine. We wanted shift tan was negative 3 divided by negative 1, close brackets, equals, and there it is, 71,5, can I round that off, 57. So 71,57 degrees. But this is only this small angle here, 71,57. What did the question ask me? Sorry, that's too far. Clockwise from the positive x-axis. So if I sketch this, this angle is sitting down here somewhere, okay? But do you agree with me that we've got to start from the positive x-axis, positive y-axis, so all the way from there, all the way around. Notice now, I need to give my answer as theta is therefore equal to 180 degrees plus that value that I worked out, 57 degrees, and I get my final answer as equal to 251,57 degrees. Let's just check that in the calculator. So to that number I'm adding 180 is equal to 251,57. That's perfect. That is the angle that is going from the positive y-axis all the way around and taking into account this extra little bit that I just worked out. Okay, so quite a lot of calculation there, but you've just got to make sure that you're answering what is the question answering. Okay,
Can I ask you a question?
Sure.
I'm so sorry to interrupt you,
no
but
problem, Megan. Go
Rapalung
for it.
asked for I, not I now. Just to quickly
Yes.
go back. Can you use the cosine rule?
I'm
asks.
sure you could, yes.
Okay.
I would imagine so.
Okay, so you can. Okay,
I'm sure you
that's
could.
all.
I would imagine so. Pythag is going to be a lot quicker.
Yeah.
And so my concern here is time.
Yes.
Is that
You don't want to just spend time
a
right.
lot of people might struggle with time. But you know, if that's going to help you, certainly you could go with that. The reality is it's going to be much quicker to work with Pythag here.
Okay, no problem. Cool.
Thank you. Sorry, I think we're jumping.
B, yeah.
Let's keep going. B. Use the component method to calculate the magnitude of the resultant of vectors P and Q. Now, I want to sketch this because I always want you to think through. You want to estimate values because when you estimate, you're actually thinking about the science that you're doing, right? So I'm going to sketch P was approximately that direction and Q was approximately over there, right? Approximately. I'm just doing a quick random sketch. But I'm getting the basic idea of these two forces. And I'm asking you, which way would the resultant go? Where would the resultant be approximately? Looking at those, surely it would be somewhere over here. Okay? Approximately. Sorry, that's not a nice arrow. That's a slightly better arrow. Okay? It would be approximately up there. The reason I do that is because I want you to be able to estimate an answer, then do all your working, and compare your answer at the end. Because it's very easy, we all know, to put the wrong value in your calculator and suddenly get something completely different. But if it doesn't match up to what you know must be the answer, then you can go back and see where have I made my mistake. So having a look at this, we're using the component method, and we are going to be looking at what would the resultant be? Now, by resultant, we are going to talk about the total horizontal. Okay, and so I'm going to write here Rx is equal to. Surely it would be the same. It would be whatever Px was. So this piece at the bottom there. Okay, we had it there already. And added to that, although it's in the opposite direction, the vector, let's put it back, the vector Q of its horizontal component. So let's put those two down. It was going to be, well, it would be the horizontal component of P plus the horizontal component of Q added together, and that's going to be 2 plus negative 3. Do you see where I got those? Positive 2, negative 3. Let's put those down, and it would be minus 1 newtons. The next part of it is I need to say, all right, what is the total vertical components? And once again, I'm going to say, this is now Ry is equal to Py, the vertical, plus Qy, the vertical. And we're going to have 4 plus negative 1. Again, we're going to find them. It was positive 4, negative 1. Added together is going to give me positive 3 newtons. Now I run out of space, but I'm going to come back and write, I'm going to extend this page, and we're going to keep working. And we have to work out the total, what was it, the magnitude of the resultant force. So let's work it. Again, I'm going to choose Pythag. Our squared is equal to the x squared plus the y squared. And that we had x squared, well, x was minus 1, so minus 1 squared plus y squared was, I believe it was 3. There it was, 3 squared. Now please, make sure that you square them, okay? Very, very important. Notice the negative is going to multiplied by the negative is going to cancel, so it's going to be 1 plus 9, which is 10. That is not my final answer. I therefore have to say r is equal to square root of 10. So square root of 10, and it's going to equal 3,16. So we can write our answer is equal to 3,16 newtons. Now, that is giving me the magnitude of the resultant vector. So how long that line is. Okay, but is that telling me yet the direction? Well, that's the next question. Calculate the direction, and remember that in this case they asked you only for the magnitude. But if they ask you what is the resultant force, then you have to always give magnitude and direction, because force is a vector, right? And a vector has both magnitude and direction. Now, once again, we need to calculate the direction. And so, once again, I'm going to go back to these two values that I worked out, okay? Rx and Ry. And they were -1. So, my diagram of this says go -1 in the x direction and go 3 positive in the y direction. So plus 3 in the positive direction. And I'm going to shift that across and draw a little dotted line here. Okay, almost a little parallelogram method if you like, to indicate to you that I'm going to slide that one across or slide that one up, and the resultant force is going to be this one, the diagonal. And we already had that 3,16 newtons. We've just gone and worked that out. Now what we need to do is work out the angle that this is at. So I'm going to choose this angle here to work out. And there are a couple of ways to do this. But I'm going to suggest we use the trig ratio, opposite over adjacent, which will be tan. So let's change pen color and continue over here. Tan of theta will be equal to opposite over adjacent, which is equal to, in this case, it would be 3 divided by -1. And that's going to be theta is equal to, let's go to our calculator, shift tan, and it was 3 divided by -1, close brackets, equals -71,57 71,57 degrees. Now, notice here that I'm ignoring the negative. The reason for that is because of the different quadrants that this is in. Don't stress too much about that. What we need to make sure is we're answering this question from what they asked us, measured clockwise from the positive y-axis. So once again, I need to sketch a little quick quad here. We have our angle somewhere up there, right? 71,57.57 was that angle that I worked out, right? We are actually working the whole thing from y all the way around, including that extra bit. What is this extra bit? 270. When we've got to work 270 plus that 71, so my final answer here for theta must be equal to the 270 plus 71,57 degrees. And my final answer then, I'm taking that value 270 plus oh, it's not wanting the 0, 270 plus 71,57 is equal to 341.341,57 degrees. Now that was quite a long question, but what you're making sure is you know how to do Pythag, you know how to use your trig ratios. They're going to help you significantly, particularly when you work with components. Megan, I think we need to take a short break.
Little bit of a break because my brain's going, what? But I know your brains are doing that as well. So a sip of water, and guys, we'll be right back. Welcome back, Mindsetters. I just want to say I'm so happy you guys are posting on the page, and I can see you are loving the show. So big 2 thumbs up to you guys because you are here for revision, and I'm pretty sure that you will get the marks you deserve because you are watching Mindset Learn Extra. But you know what, guys? If we don't get to your questions, please go to the help desk. You know where that is? It's not Learn Extra. It's mindset.co.za/help desk. Learn Extra is the webpage. So help desk. We also have an app that's posted for the Facebook, and you guys can get it on Mixit. So if there's any question that we don't get to in this time, because we only have a short amount of time to get through everything, please post it on Help Desk, and I promise there will be answers. So Tracy, carry on with our revision, please.
Thanks, Megan. So we're going on to the next question, question 2. In an experiment to determine an unknown mass of an object, 2 100-gram masses and an object of unknown mass are suspended from 3 strings. Now I want to just slide down and show you the picture. There we've got our unknown, so I'm going to put a question mark next to that, and we've got these 100-gram masses that are pulling on the strings. Okay, so let's keep going with the question. As shown in the diagram, not drawn to scale. The strings are light and inextensible, meaning they can't stretch. Okay? 2 of the strings run over frictionless pulleys, which means that they're going to, a frictionless pulley is this round thing on the side. Whatever the force is pulling down on the mass, which is going to be the force of gravity, that same force is just going to have its direction changed. So the force of gravity pulling down there is actually going to be pulling upwards there because the string is pulling over these 2 pulleys. And in the same way, there and there. When the 3 forces acting on knot O, which is in the center, there it is, are in equilibrium, key important word NB, we need to explain equilibrium. The angles between the strings and the vertical are 45-degree angles each. So if I jotted down a little dot there, that's a 45-degree angle, and that one's a 45-degree angle, as shown on the diagram. So we've understood what's happening in this diagram. Let's get going with the question. Define the term equilibrium as used in this experiment. So what do they mean by equilibrium? Equilibrium means forces are balanced. Okay? There is not going to be any acceleration in this object, forces are balanced, and we can simply say F res is equal to 0. There will not be no resultant force. Write down the most important experimental error that can occur when conducting this experiment. Now I want us to think about how we're going to do an experiment like this. We're going to have a force board, we're going to have these pulleys on the side, and we're going to be allowing it to stabilize, so the strings are going to stabilize. What do we need to be able to use to work out the forces? We're going to measure those angles, all right? And how you're going to do that is you're going to put a piece of paper behind and then allow the strings to be sitting against the paper. Now, if I read it from the side like this, there's no way that I'm going to be able to accurately measure that angle. Or if I'm measuring from above or below, it must be directly in front of your eye, okay, so that you can very easily pinpoint where the angles are, where the forces or the strings are positioned, so you can measure the angles very, very accurately. So here you're thinking it's going to be the error of parallax. If your eye is not perfectly lined up with those strings to measure those angles. Now we are asked to draw a force diagram showing all the forces acting on knot O. Sorry, let's go back here. I don't want those, I want this. We're looking at knot O. Indicate the magnitude of each force on the diagram. Now I'm going to shift this down to the bottom of the page to give ourselves space, because we're going to need to draw lots of forces here. So draw a force diagram showing all the forces acting. I'm going to start with a little dot in the center. That's going to be force. That's going to be the knot O. And we need to draw some forces. What force do you start with? This picture looks scary. What am I going to do? Okay, it's not that scary. Start with the simplest one. And the simplest one, in this case, is gravity. I always say to my students, start with the force of gravity, because you know it's going to be straight down. And whatever other forces are, they will always be in reference to that lovely vertical that is straight down, the force of gravity. So let's continue down and draw the force of gravity in at the start, and I'm going to go straight down, capital W for the force of gravity. What other forces do we have? Well, we've got the two strings pulling up at a 45-degree angle. So we've got, let's just undo that, scribble. We've got that one, and we've got that one. Now, obviously, I'm drawing by hand. You would have, be using a nice ruler, but you're very clearly showing 45 degrees in the spaces as those angles. Now we need to label this thing. We've labeled W. Now we need to label the other two. And I want you to think about the fact that you're labeling these, but you also wanted to show values. So having a look at what we had, did we have labels? Well, we had 100 grams. The mass of each of these was 100 grams. Now that's a very, very important value, a very useful value. So I can go down here and say, all right, well, W for, or better yet, let's call it tension in string number 1 must be equal to the mass times gravity, the mass of 100 grams, which I would convert to kilograms immediately. So 100 grams divided by 1,000, going to give me 0.1 kilograms. Multiply that by 9.8. And I'm going to get 0.98 newtons. If you want us to check that, 0.1 let's do 100 grams divided by 1,000 is multiplied by 9.8 is going to give me 0.98 newtons as the value. So this value over here is 0.98 newtons. Because I know that the other string also had a mass of 100 grams weighing down on it, I could also add in this side 0.98 newtons. And I think we've now filled in as much information as we know about that, this force diagram. Let's keep going with the next question. We've drawn the force diagram, perfect. And we've indicated the magnitude of the forces that we know on the diagram. Part D of the question asks us to calculate the unknown mass m. So we're going to work out the last force, in a sense, working out the weight. Determine by accurate construction and measurement or calculation the unknown mass. Now, you've got options here. They are telling you either draw it very accurately to scale, all right? Or they're saying calculate it. Now, I'm going to go through the calculation. But I want you to know that if you have a nice ruler and you've got your protractor, you can go and measure the angles and draw this very accurately. So they tell us to use a scale, and I'm going to sketch it for you, but I'm asking you to make sure that you would be able to do this both ways, right? So you can choose which is easiest for you. Now, the force diagram that we've got, we need to work with, to draw up a triangle. Now, do you agree with me that this triangle is going to be a closed triangle? It has to be a closed triangle. Why? Because these forces are in equilibrium. There is no resultant force. Okay, so it has to be a closed triangle. And I want to start with the weight, but that's the unknown. That's what I'm going to find. So actually, I'm going to start with drawing a vertical, and I'm going to draw it as a dotted line to start. Then at the bottom here, I'm going to put a little cross, and I'm going to start by measuring a 45-degree angle there. That 45-degree angle, I would be able to measure with my protractor, and we would have this one as 98 millimeters through using your ruler. Why 98 millimeters? Well, because they gave me a scale to use, and 10 millimeters was representing 0.1 newtons. So using those two values, 0.1, 0.1. What is the angle between the two? Sorry, that needs an arrow. What is the angle between that string and the tension in the next string? It should be a 90-degree angle. So you're going to have the next one going up, and that's a 90-degree angle. And that's also going to be 98 millimeters, drawn to scale. And then the last one that you would need to note is this is going to be all the way through to the bottom, and that would be the weight. And you would be able to measure that, and I think it comes out to 138.6 millimeters if you do it nice and accurately. Obviously, there is some leeway, but make sure that you're measuring accurately those angles. Now I want us to talk, and very clearly, this is a closed triangle. Now I would like us to talk through the calculation, okay? Because the calculation is going to be more accurate because you're not dependent on your own drawing skills, but you can use your maths knowledge. And I want us to think about what it means when we say something is in equilibrium. If it's in equilibrium, it means that the angles, the sum, that's the symbol for sum, of the forces in the y direction is equal to 0. And it also means that the horizontal forces are also equal to 0. But specifically here, I'm speaking about the vertical forces. Because if you think about this, the upward forces of the string must balance out the downward weight of that unknown mass. Okay, so I'm going to sketch the picture very quickly. Those are the two strings and the downward force. Now what I want us to think about is if I'm going to take this one as the upward force of string tension number 1, and it's going to be tension number 1, y. And that one will be tension number 2, y. Those two added together must balance out the downward force. So how do we write that? We can work, and we can say, we can work out each of these. So let's do them separately. I'm drawing a little dotted line. I have this value, sorry, let's just rather write that in a different color. This was 0.98. This angle here was 45 degrees, which means that one inside there is 45 degrees. I've got alternate angles there. 45-degree angles, so it's actually going to be quite easy to work with. Here in this case, I've got adjacent over opposite. So I've got cos of 45 degrees is equal to, and it's going to be adjacent over hypotenuse. Adjacent over hypotenuse, which is going to be giving me adjacent is equal to the hypotenuse multiplied by cos of 45 degrees. What is the hypotenuse? It was the 0.98. So 0.98 multiplied by cos of 45 degrees. let's go to our calculator. So I'm saying 0.98 multiplied by cos of 45 degrees equals, and I get there 0.692 is equal to 0.692 dot dot dot. We're going to keep it in our calculator and we're going to come back to it. That, by the way, would be in newtons. That's an upward force. Do you agree that the angles on each side were the same? So actually what I've got when I write this out is I'm going to say mg cos of 45 plus mg cos of 45. Where those are coming from? Well, I've just worked out the one would be T1y plus T2y. Mg was the 0.98. Okay. Those together must be the same as the mass times the gravitational pull of this downward force. They're going to be opposite signs, but they must be the same in terms of magnitude. So I have, in theory, actually got 2 multiplied by this 0.692 dot dot dot, whatever it was, is equal to the mass, which is unknown, multiplied by 9.8. So I'm going to go back to my calculator because I've kept that number in my calculator, and I'm going to say that times by 2 is equal to 1,3859. So we're going to go back here, and that was 1,3855 something, 3859 dot 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 is equal to the mass times by 9.8 divide by 9.8, and I'm going to divide both sides by 9.8, and so the mass must be equal to how much? We divide that by 9.8 equals, there we have 0.141 etc etc units, kilograms, because I'm working in SI units. Is that a very nice number? Probably not. Let's divide that by 1,000. So I'm going to go back to my calculator, divide by 1,000 equals, and there we have 1,1. So I think I would times by 1,000. So go back there, 0.141 times by 1,000, because I want to get it to grams, and it's going to give me, and I think the final answer, mass would be 141, I think it was 42 grams would be the mass hanging on that unknown mass. We need to take a short break, and we've done question 2. So deep breath, go over it, revise it, because it's a very, very important question. Megan.
You ready for a break? Okay, mindsetters, you know what time it is? It's break time. So don't stress, don't fear, don't go anywhere, and we'll see you right afterwards. And welcome back, mindsetters. Hope you had a good break, you got refreshed, you got everything you needed to do, because right now you guys are ready to rock some physics, because I know I am. So Tracy, let's go.
Thank you so much, Megan. So we're going to skip to question 4. So try question 3, but on your own time, but I specifically want us to go through question 4 because I'm sure this is going to be a question that lots of you are going to ask me questions about. So we've got this idea of a skier going down a slope. It's a question that students often struggle with, so I specifically want us to do it. A skier of mass 60 kilograms skis from rest. What does that mean? That means VI, or the initial velocity, is 0 meters per second. Down a slope inclined at an angle of 15 degrees. Again, very important. The length of the incline is 75 meters. He reaches the end of the incline at a velocity of 15 meters per second. That is my final velocity of 15 meters per second. a constant frictional force, so there is friction in this case, acts on the skier on his way down. So there he is skiing down the slope, and we've got angles, we've got vectors, we've got plenty going on here. And we've got friction. Write down an expression for the magnitude of the normal force acting on the skier and then calculate its magnitude. So what I need us to do is draw out the scenario, all right? Let's have a look, and I'm going to change from being quite a complicated skier drawing. I'm going to draw, so this is going to be part A. I'm going to draw it just as a box on a slope, okay, because a box is easy. So once again, we've got our slope, and there's the box on the slope. In this case, it's a skier. There he is, okay? He's going down the slope, and we need to talk about the forces that are acting on him. Are you agreeing with me that there is going to be the force of gravity acting straight down? W, or F small g, is acting straight down on him. Then that force of gravity can be split into its components, because if you think about it, gravity is always pulling you to the center of the earth, so straight down. That force of gravity, though, can be split into components, and you've got a component that is parallel to the slope. That's not an 11, that's a parallel sign, and a component that is perpendicular to the slope. Okay, perpendicular means at right angles to the slope. Now, having a look at that, we're going to think about the normal force, because I'm going to break this scenario down, and we've got the angle in there of 15 degrees. You can work it out mathematically. It's going to be 15 degrees in that little angle in there. Now I want us to think about what we can do in terms of working this out. They are asking us specifically about the normal force. Now, the normal force is a force acting from this body, acting up. And I haven't given myself much space here, but that normal force, if you think about it, it's the surface pushing up on the object. How much will it push up? Well, it would push up, according to Newton's third law, based on how much the object is pushing down on the surface will push up on the object. So as object A exerts a force on object B exerts an equal but opposite force on object A. So as the skier is pushing down with the perpendicular force, it's going to be the normal force is acting up. Okay? And so we can write the magnitude of the normal force is equal to the magnitude of F perpendicular. So I want us to go and find out what F perpendicular would be, right? F perpendicular is what we need to work out. So I'm going to just take that away and write in here what we have. We're going to work with standing there at 15, adjacent over hypotenuse. So it's going to be cos of 15 degrees is equal to adjacent over hypotenuse. Do you see how important your trig is? Adjacent, which is actually F perpendicular, is equal to the hypotenuse multiplied by cos of 15 degrees. So F perpendicular, which is what adjacent is equal to FG times cos of 15. And I can continue that by saying, okay, that is the mass times gravity times cos of 15 degrees. What was the mass times gravity? Because that's what we were asked to work out, is equal to this man was 60 kilograms, gravity 9.8 times cos of 15 degrees. And we can go to our calculator and write in there 60 multiplied by 9.8 multiplied by cos of 15 degrees is equal to and we get there 567,96 is equal to 567,96 newtons. And therefore, I can say, therefore, the normal force is equal to 567,96 newtons, because the force that's perpendicular on the ground is going to be the same force as the force that the ground is pushing up on that object, or in this case, the skier. So let's continue. We have done question A. Write down an expression. Let's go to question B. Draw a labeled free body diagram showing all the forces acting on the skier as he skis down the slope. So I've started it, but I haven't quite finished it. So let's give ourselves some more space. We've got the object, force of gravity straight down, Fg. Then we had the second part, the normal force. The normal force. Then we also have another force, and that is the frictional force. And this is kinetic friction, because specifically that skier is moving down the slope, so it's the force of kinetic friction. Are we happy with all of those? We've got gravity acting straight down, we've got the normal force perpendicular at 90 degrees to the slope, and we've got the kinetic friction going parallel to the slope, up the slope, slowing the skier down as he's going down the slope. So that was part B. We've drawn that. Now we need to calculate the frictional force acting on the skier during his motion down the incline. Now I want us to go back to this question and notice a whole bunch of information. We had velocity values, and we had a distance value, and we've got this mass. So let's go and write down as much information as we can, because that's going to help us decide what we're going to do. So I'm writing there A equals, question mark, V final equals, that was 15 meters per second, and I'm going to choose down as positive. Remember, it's so, so important to make sure that you choose a direction. It's not liking my fast handwriting today. There we are. Down as positive. Okay. V initial was 0 meters per second. What else did I have? I had delta x was the distance, and it was 75 meters. Now, looking through those values, you might say, well, why did you write all that down? Well, it's going to be helpful to me, because at this stage I don't have the resultant force, and that's one of the values I'm going to need to use. Okay, so notice here I've got a lot of information, and I can use an equation of motion to go and find the resultant, the acceleration, which will help me find the resultant force. So let's go with an equation of motion. I'm going to use V squared. V final squared is equal to V initial squared plus 2a delta x. Let's plug in the values that we have. 15 squared is equal to 0 squared plus 2a delta x was 75. Notice all of those are positive because I chose down as positive, and they're all acting down. So plugging in those values, we have 15 squared is 225. Check it. 225 is equal to 0 plus, well, 2 times 75 is going to be 150. 2 times 75, 150a. Now I'm solving for a, so I'm going to divide both sides by 150. Let's just undo that, because a would be 150. A is equal to 225, so a must be equal to 225 divided by 150, and that comes out at 225 divided by 150 equals 1.5. 1.5 meters per second squared, and I have to give a direction. It is positive, so it's acting down. Now that's going to be very helpful to us because we're wanting to use the acceleration to find the resultant force, and I'm going to go and plug in this to Newton's second law. This is from Newton's second law. Resultant force is equal to mass times acceleration. Do I have the mass? Yes, I do. Do I have the acceleration? Yes, I do. So we can go and use this to calculate Newton's second law. Another way of working out the resultant force is adding all the forces together, and it's going to be the total overall force. So the next thing I want to say is that must also be equal to F parallel plus F kinetic. Notice these are the forces that are acting in that plane. Okay? And so we've got here the parallel component. Now I don't have the parallel component yet, so I'm going to shift up slightly. I'm going to change pen color so you can see. I'm now going to work out F parallel, and I'm going to just do that in a little box. And I'm going to go back to this diagram and have a look. F parallel is there, so it's opposite, which is sine over hypotenuse. So sine of theta is equal to opposite over hypotenuse, which is going to mean opposite is equal to the hypotenuse multiplied by sine of 15 degrees, and we're going to work that out, and that's going to come to, well, mass times gravity times sine of 15, and you can go and solve for that and work out the R parallel, then go and plug those values in, and you can solve for this unknown, noting that you can put in 1.5 meters per second. You've got squared, you've got the acceleration. Now, vectors and Newton's second law, all of Newton's laws can be quite confusing. Make sure that you sketch a diagram of the situation, because if you do that, it will really, really help you to interpret what the question is asking, to make sure that you've got direction, and always, please, 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 always give units for everything that you do. Okay? Make sure that you do not throw away marks by leaving out direction in your final answer if it is a vector quantity. Okay? These are simple things, but they're incredibly important because you're always talking about physics. So that's all from me. Thanks so much. Megan, over to you.
Thank you, Tracy. Thank you, as you guys are calling yourself pre-matrix. It's been great having you on the show. I'm so excited to see how much you've learned. Thank you for posting on the page. Thank you. Don't forget about the Samsung competition. Please, please, thank you guys for joining in on our show. Have a fantastic evening, Oaks. That's from me to you. Cheers. I'm out. Bye.
We're going to draw over it. That is vector P. All right? And it says to me, use a calculation to work out the magnitude of vector P in force units. Well, what do I have? I basically have, and I'm going to sketch it for us here, I basically have, if that is P, I'm going to work out the bottom of this triangle is in 2 units, and the side of the triangle going up there is 4. I'm just reading off those values off the graph. So if I sketch that again, and I'm literally just sketching, this side was 2 and that side was 4, I can work out the magnitude of the vector P. The magnitude I'm going to work out through Pythag. Okay, Pythagoras, all right, you know it. R squared is equal to x squared. R squared is equal to x squared plus y squared. What do I have? I had x was 2 squared plus y was 4 squared. Let's work that out. Well, 2 squared is going to be 4, plus 4 squared is 16, is 20. Is that my final answer? No, it's not my final answer. I need to say, well, r, which in this case is actually p, is going to be the square root of 20, and I can't leave my answer like that. I have to square root it and show it in surd form. And so we go to our calculator and say square root 20 is equal to, and I don't leave my answer like that, I write it as a decimal, 4,47. So 4.47 in force units, newtons. The direction of vector q is the next thing I need to calculate. So I'm now going to be asked to calculate, that is theta, the direction q, measured clockwise from the positive axis. So once again, I'm going to sketch this, and q went off somewhere this way, and if I have my
new content updated every single day. So here you can see it's physical sciences, and I'm sorry, but Tracy's just a little bit. So here we have the notes on this side, obviously, and the video. So how amazing is that? You get content, you test yourself for revision, and the video you can watch on the lesson. That's really, really cool. Other than that, guys, it's only for premium smartphones and Samsung tablets. But stress, not mindset, is because you know about the Learn Extra Exam Revision Marathon competition, right? Yes, you do, because all you have to do is download the notes. I'll post the link for you now, and you click on the race number, you look at it at the bottom of the notes, and then you enter it into the link. Okay, the link will be posted on Facebook as well as the revision notes where you have to find them. So it's basic, it's easy. You enter your name once and you get thrown into 9 draws. How amazing is that? So it's awesome, cool. You could stand a chance to win yourself a tablet. So then you can actually download the Learning Hub app. How cool is that? So without me just rambling on about this, Tracy's going to take it away with Newton.
Thanks so much, Megan. So we're going to be carrying on with forces and Newton's laws. Let's get straight into this. In this lesson, we're going to revise how to work with vectors. And vectors are something that students often, they say to me, I can't stand vectors. Vectors are so useful. But you've got to know how to interpret them and how to use them. And then we're going to be looking at applying Newton's laws to a whole bunch of different scenarios. Specifically, we're going to be tackling questions. So let's get straight into it, because I know grade 11 revision, this is very important for you. So we have been given 2 force vectors. This is question 1. There are force vectors. So immediately you're going to be thinking to yourself, whatever units I have here are going to be, the units will be in newtons. Okay, N. The force vectors P and Q were drawn to scale on the Cartesian plane. The fact that they are drawn to scale is also something very important. It means I can take the measurements from them, which is very valuable. Use a calculation to determine each of the following: the magnitude of the vector P in force units. So, having a look at this diagram, I've got quite a bunch of information. Let's have a look at it. This first one, and I'm going to draw it in blue.
Welcome, grade 11s. Yes, you are here with me, Megs, and of course, my lovely lady, Tracy. But we haven't been together in so long. It's so sad.
I know.
So tragic. Please tell me what we're doing today.
Today, we are going to go through forces and Newton's laws. And as we were talking just before the break, it's really a critical section of work, and it's a section of work that students often struggle with. So today is a good one to tune in.
Like I told Tracy just before we started, Newton's laws were not my favorite, but they are really important. Definitions, most important, as well as arrows and this and vector and this and everything. So I suggest you grade 11s take note, because especially for matric, this is a section that hits you hard, I promise you. But anyway, I have to tell you about the Samsung Learning Hub app that has been sponsored by Samsung, obviously. powered and sponsored proudly with Learn Extra Mindset. So let me just show you how it works, what it's all about. It's the Learning Hub. You guys have heard about it. Free content as well as